Hello boys and girls, Mr. Giomini. I wanted to apologize first of all for not being in the classroom today. I am in the building, just it's professional development, trying to become a better teacher, which I always need to do. Anyways, today what we're going to do, and think about outlining the entire week here for us. Today we're going to work with another article from Scholastic Math Magazine. I like this article we're doing today. It's called A Truer Blue. We'll work with it for next today and Wednesday due to the air testing for social studies tomorrow. I won't see many of you, but I like this article in part because it shows you that somebody, they stumbled upon something that was new and never discovered before by accident. And I think sometimes, even in mathematics, I think sometimes we make a mistake and we get down on ourselves. But it also shows you that making mistakes sometimes lead to great discoveries. And this is true of science, mathematics, even history, where you might be unearthing something and come upon something that you didn't think you were going to discover. So don't ever allow yourself to be, should we say, dissuaded or kind of feel like you had a setback, because your setback may lead to new discoveries. So always want to try to push your way through things, because it'll lead to something newer. So A Truer Blue really talks about ratios and how ratios can be used to create new colors. And that's really this article is about, creating a new color. And it's really a blue. This actually is the color. And we're not used to seeing colors like this. We're used to see crayons or in a magazine ad or on TV. But this is where the color really starts. It's almost like a powdery, like blue powdered sugar. But I want to take a look first. It says what makes up this. And the color is, it's difficult to pronounce. It's not a word that you and I typically use. But it's called, the chemical molecule is, it's Y, and then INMN. It's yttrium, indium, manganese. And I believe you were working with elements in the periodic table with Mrs. Demko in science. So this is a nice crossover. You see the connection between both science and mathematics. Now the sub is going to really briefly here play a video for you that interviews the gentleman whose lab they uncovered this new color in Oregon State. And what's nice about this video too, it lets you boys and girls see what awaits you possibly if you want to go and head into college and really delve into the sciences. So we could pause, if you want to pause this video right now, go to the YouTube video that I already have keyed up and watch the video. Alright, and we'll continue to discuss when you get back. Alright, now hopefully you enjoyed that video and kind of got a little flavor for what this gentleman did in his lab there. Now, we talk about yttrium, and here it is on the periodic table, and this is actually what it looks like in its raw state, what you might find it when unearthing it. And I know you guys talked about strip mining, open mining, and I believe there was one, deep mining possibly. I apologize for not knowing all three. But this is what yttrium will look like if you were mining it. So it almost looks like a piece of artwork to me, like a piece of petrified wood. Really neat in its structure and the way it's layered and in the overlapping. Very, very unique. This is indium. Now, again, periodic element 49 on the periodic table. This almost looks like a piece of something you discover on the moon, some moon rock or something of that nature. Very nice. It very much looks like the yttrium. And we see these two, they're silver in color. You want to think about it, well, how does it all of a sudden become blue? And then the final one, we have yttrium, indium, and manganese. And manganese looks like this. Its periodic number is 25. We're talking about the number of protons, electrons in it. There's a symbol name, atomic mass. So same things for back here. The way, oops, sorry about that. The way you had here. But again, it's a dark kind of silver grayish color. Think about it though, when they apply heat to these things, that's what changes the composition of these. And you've probably talked a little about that with Mrs. Demko. When heat or pressure is applied to these elements, they begin to change in their properties. And I may be misspeaking here, but their properties begin to change. Now, what we want to talk about with this, and I'm going to read the article with you in a second, but we're going to be analyzing and kind of focusing in on chemical formulas. And this is Na2SO4. We call that bisodium, let's see, sulfur oxide, I believe, or something like that. Now, we see the different number of atoms that each one represents. Now, this sulfur has no numbers subscripted below it. So that means there's just one atom of sulfur. Here you see the 2 subscripted below the sodium, the Na. That means we have 2 sodium atoms. Here we have 4 atoms of oxygen. And we'll be talking about writing ratios with this stuff. Alright, writing ratios with this. Now, I'm going to go to the article. Here is the article. If the sub would do me a favor and hit play here, we'll be able to watch a quick video that just reviews what ratios are. We haven't touched on ratios in a while. So again, if you wouldn't mind pausing this, playing the video, and then resuming back once the video is over, I'd greatly appreciate it. Alright, now that we're back, I'm going to make this a little bit larger. First thing I do is look at the illustrations here. It says a history of blue. Yttrium blue is the latest in a long line of blue pigments used throughout the history of art, clothing, and jewelry. And many of you might have a pair of jeans at home, I know I do, that are blue, and they just don't come that way. They must go through some kind of chemical and dyeing process. We see here we have the indigo dye. Now, I think you've probably talked a little bit about this in social studies with Mrs. Spagnola. So again, nice crossover. We see that indigo dye back from 4184 BCE. So we're talking almost over 6,000 years ago. And it's best known for giving denim jeans their signature blue. Indigo dye is made of wad, a plant common in Asia and Africa. It was introduced to Europe in the 15th century, but has been used for thousands of years. So it's something that jean manufacturers are still using today, something that really has its roots almost 6,000 years ago. We have the Egyptian blue, and I'm sure you talked about this in your Egypt unit with Mrs. Spagnola. This goes back to about 2500 to 2400 BC. The first artificial blue pigment was created in ancient Egypt. It's made by mixing sand, copper, and natron, a type of salt, and then heating the mixture. Again, applying heat will change up the chemical properties of these things. We have ultramarine, and that's from 500, 600 CE. So we're now talking about not necessarily 6,000 years ago. We're talking roughly about 1,500 years ago. The original pigment was made of semi-precious stone lapis lazuli, which was ground up and purified. It was later imported into Europe, earning it the name ultramarine from the Latin for beyond the sea. Oh, Latin stems, again tying with Mrs. Moore. If I continue to kind of go up here now, we have the Prussian blue, circa 1706. The first modern synthetic pigment was discovered by accident. Again, another accident. We see here, there's two kind of examples here where scientists trying to do something in a lab, and all of a sudden, by accident, they make a new discovery. So this goes to show us that not all accidents are bad. Discovered by accident when a chemist who was trying to make red added a mixture that included the chemical cyanide to his paint. Today, the color's name refers to the coats Prussian soldiers wore. We have cerulean, and this is in 1789. Excuse me. So shortly after the end of the Civil War, about 20 years after. Made of copper and cobalt oxide, this pigment produces a sky blue color, but it can turn green or fade. The name cerulean was used 200 years before they made the pigment. We have cobalt blue. Natural cobalt, based on the metal, has been used for centuries, most notably in Chinese porcelain in the 8th century. But the first synthetic cobalt blue pigment was made by French chemist Louis Jacques Thénard. And then we have, I'm going to try to pronounce this, phthalo blue. And this is really less than 100 years ago. We're talking about, let's see, 70 of it, 2000. So we're talking about 87 years ago. Not a long time ago. My grandparents were born roughly around this time, a little bit before this actually. Phthalo blue is a brilliant light blue used in inks and solar cells. It's made of copper and a chemical called phytolacicyanide, I believe. Now, this is here what we're going to work on with tomorrow. Oh, yeah, here we go. We're talking about how to write these chemical formulas, but then also to analyze and create a ratio. So it says here are the numbers of each type of atom in the formula. So we have yttrium, which we have one atom. We have the IN, which, what was the IN again? What did the IN stand for? Let's see if anybody recalls. I'm trying to think myself. What does the IN stand for? Indium there. Indium. Now we have two atoms here. We have one atom of indium and one atom of manganese. And then we have O, which we should all know O is oxygen, three atoms of this. So this whole chemical formula is created of 1, 3, 6 different atoms. Now it says part to part. So we're comparing one element to another element, not one to the whole chemical formula. So it's what's the ratio of B metal atoms to oxygen atoms. Now, this isn't a bracket to denote that is a metal, a B metal specifically. Not quite sure what that means. I'll have to Google that, look that up myself. But we have 1 and 1, so that gives us 2. So we have 2 parts B atoms and then 3 parts oxygen atoms. All right, part to whole. So we're carrying 1 part to the entire thing, which also includes that part we're analyzing. So the first term, what is the ratio of yttrium to total atoms? Well, yttrium has 1 atom in the total of 6 atoms. Part to whole, what is the ratio of total atoms to oxygen atoms? Here we're going the whole thing to the part, but the part we're talking about here in the second term also is part of the whole. So whole to part, we have 6 total atoms to 3. All right. Now, rather than actually, you know what? I wasn't gonna read it, but why don't you and the sub read this together? All right, read this together. And once you're done reading here, I already have a Socrative up and running for you. Remember, it's gonna be Troy 606. Once you're done reading and discussing this, Troy 606. What I would like to do today for your username, all right, for your username, and we'll talk about this tomorrow. For your username today, rather than just putting your last name, whatever class period you have me, so believe today it's going to be 1, I would like you to do an underscore. So if you hit shift and the key next to 0 on your keypad and then your last name, all right? If you're in second period, obviously it's 2, underscore, and then if you're in third period, it'd be 3, underscore, all right? That way I can sort it by class period. Okay, hope you're able to do this and handle this well. Hope you enjoy the article, find it interesting, as interesting as I did. And we will see you guys later today because I will be in the building, but we'll talk more about math tomorrow in class. Okay, so you're going to read the article, and then once you're done reading the article as a class, I will then have the Socrative up and running, and it's going to be on topic 3 today. Topic 3. Okay, take care. Bye-bye.